Okay, let's dive right in. We talk a lot about solar and wind power, but there's this other massive source of energy out there, one that's driven by the moon itself. Today, we're talking about tidal energy. It's a pretty wild question when you think about it. Every single day, there's this cosmic engine, almost 250,000 miles away, pulling on our oceans. The amount of power is just staggering, but figuring out how to actually harness it, well, that's a whole other story. So here's the game plan for today. We'll kick things off with the basic science, then get into the nuts and bolts of the engineering. After that, we'll look at how you even find a place to build one of these things, weigh the good against the bad, and wrap up with the biggest challenge of all, the environmental side effects. All right, first things first, before we can even begin to talk about turbines and power plants, we've got to understand the force we're trying to work with. So what is tidal energy? Well, at its core, it's a kind of hydropower. But instead of using a river flowing down a mountain, we're tapping into the massive vertical movement of the ocean itself, that constant rise and fall of the sea level, and turning that into electricity.
Now this is where it gets really interesting. Yeah, the sun's huge, but the moon is so much closer that its gravity is the real star of the show here. It accounts for about 3/4 of the tidal pull. It's like this cosmic tug-of-war that creates these bulges of water on opposite sides of the Earth, which gives us our steady rhythm of high and low tide.
And this number right here, this is the secret sauce for tidal power. Think about it. Solar power depends on the sun shining. Wind power depends on the wind blowing. But the tides, they run on a clockwork schedule set by the moon. We can predict them with incredible accuracy decades into the future. That kind of reliability is gold for a power grid. Okay, so we've got this super predictable rise and fall of water. How in the world do you turn that into usable power? Let's get into the engineering. This diagram really shows the basic idea perfectly. It's almost like a giant dam or barrage. When the tide comes in high, you open some gates and let a huge basin fill up with water. Then, you shut the gates, trapping all that water. As the tide goes out, you've got a massive difference in water level. You just release the water from the basin through turbines, and boom, you're generating electricity. Let's take a closer look at this setup, because it's the most common. You can see all the key pieces here: the main dam, the sluice gates that let the water in, and the powerhouse where the turbines live. It's a really clever design, but it does have one catch. You're really only making power in bursts when that tide is going out and you're emptying the basin. So to get around that stop and start problem, engineers came up with this, the double basin system. It's exactly what it sounds like. You have two basins. One acts as a high-level pool that you fill up at high tide, and the other is a low-level pool you empty at low tide. Then you can generate power almost all the time just by letting water flow from the high basin to the low one. Pretty smart, right? So at the end of the day, it's all about this trade-off. A single basin is way simpler and cheaper to build, but your power comes in pulses. The double basin? It's a lot more complex and expensive for sure, but it gives you a much steadier stream of electricity, which is way more useful for the power grid. All right, so the technology is solid, but you can't just plop one of these massive structures down anywhere. Finding the right spot is like solving this incredibly complex puzzle where you have to balance raw power against some serious practical and environmental hurdles. This is it. This is the billion-dollar question, literally. It's not just about finding a place where the tide is really high. It's about a whole laundry list of things that all have to line up just perfectly. So here's the engineer's checklist. You need fast-moving water, which means more energy. You need the water to be deep enough to actually build the thing. And this one's huge. You need to be pretty close to the coast, because running those giant power cables miles and miles offshore gets expensive fast. That's why you always see people looking at narrow channels and estuaries. But just when you find what looks like the perfect spot on the map, you have to pull out a totally different map, the ecological one. And it turns out a lot of those perfect spots, those estuaries, are also incredibly important protected ecosystems. Trying to get permission to build something in a marine protected area is, as it should be, a massive, massive challenge. And all of this brings us to the bigger picture. We need to take a balanced look at this technology, because while the advantages are pretty amazing, the drawbacks are really serious. The pros are super compelling. I mean, it's totally renewable, it doesn't create greenhouse gases, but its killer feature, like we said, is that predictability. Power grid operators absolutely love it. And these things are built like tanks. The La Rance plant in France has been chugging along since the 1960s. That tells you something about how durable this tech is. But on the flip side, the cons are just as big. The upfront cost to build one is astronomical. Even the best designs aren't perfectly continuous. And as we've seen, there just aren't that many places in the world where this can work. But it's that last point that we really need to zoom in on, the environmental impact.
Because the thing is, when you build a giant wall across an estuary, the effects don't just stay put. They create a ripple effect that can actually change the physics of an entire sea.
Okay, check this out, because this is kind of mind-blowing. This shows what's called the far field impact. The map on the left shows the tides in the Irish Sea as they are now. The one on the right, that shows how the tides would change after building a few barrages. You can see the tide heights changing hundreds of miles away. You're not just affecting a local bay, you are fundamentally changing the hydrodynamics of the whole region. Now, back at the actual site, the most immediate impact is this. You basically change the water levels inside the basin for good. That means you end up flooding areas that used to be exposed mudflats or salt marshes at low tide. And those intertidal zones are incredibly important ecosystems, especially for birds and other marine life. And this chart really puts that loss into perspective. It shows how much of that vital intertidal habitat would just disappear. If you look at some of these proposals, you could lose half of the existing habitat. This isn't a small tweak. It's a complete transformation of the local ecosystem. So, is there a fix? Well, sort of. There's an engineering trade-off. You can use a more sophisticated system that helps preserve about 3/4 of the original habitat, which is great. The catch? It makes the electricity, which was already really expensive to begin with, even more expensive. And that really leaves us with the core dilemma, doesn't it? We have this incredibly powerful, clean, and predictable energy source right on our doorstep. But to get to it, we might have to fundamentally re-engineer huge parts of our coastlines, with consequences that we're only just beginning to understand. It's a massive question for our energy future.